Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to write the null solution for a second order linear differential equation that has complex roots. And we're going to try an example. So here we go. We're going to solve y double prime plus y prime plus y equals 0. Now remember our characteristic polynomial. Characteristic polynomial is s squared plus s plus 1 equals 0. And the solution to this one, this won't factor, and it's not obvious, I don't think, so we're going to write it as s. And remember, this s without a subscript represents s1 and s2. So this is going to be a -1 plus or minus the square root of 1 squared minus 4 times a times c. Both of every coefficient is 1, and divided by 2 times 1. We clean this up. This becomes -1 plus or minus I square root of 3, because 1 squared is 1 minus 4 times 1 times 1. Well, that's going to just be -3 square root of -3. It can also be written as I root 3 all over 2 times 1, which is 2. So here it is. This is it. So S1, I'm going to write it this way as -1/2 plus I root 3 over 2. And S2 is -1/2 minus I root 3 over 2. I know, once you've solved this in general, you could plug all of these back in and expand everything, but what we just learned was that the null solution for complex solutions is some coefficient c1 times e to the at cosine. In the last example, we called it b, lowercase b, but in this case, it's usually omega t plus c2 e to the a t. I think there's a fly flying around. Sine of omega t. Well, in this problem, what do we have? We have, let's come up here, we have that a is -1/2. And our omega is the square root of 3 over 2. And so there we have it. We can say that our null solution is c1 e to the -1/2 t cosine root 3 over 2t plus c2 e to the -1/2 t sine of square root of 3 over 2 times t. So you might wonder, well, what does this describe? How would you graph that? Well, you've got two parts going. The most influential part in this problem is that you have the exponential function. And in this case, since the exponent in the exponential is negative, you have a decaying solution. So let's just think of it this way. If you have e, the graph of e to the -1/2 t, well, that's going to look something like this. That would, just by itself, is going to be something like this. Here's 1, and it's decaying. Well, we'll just go with the first. I'll make this better graph. There. So I have something that looks like this. Okay, that's just the exponential by itself. But now you have cosine and sine. And remember, those are oscillating functions. However, they're all being multiplied by something that's getting smaller and smaller and smaller. So what happens then is your null solution has some initial condition that it starts at. Maybe it starts, we'll call it, maybe it starts, well, we'll give it the same one. This point here, instead of calling it 1, this could be my y of 0. This is my starting point. So what happens then is your solution is going to be decaying and oscillating at the same time. So it's going to oscillate, but each time it oscillates, it gets a little bit smaller, smaller, smaller. And that's what that picture looks like. When the exponent of the exponential is positive, then you have something that's growing, oscillating out of control. So this blue one here, will say it is a less than 0. And if you have a greater than 0, you're going to have a function that's going to pass through its initial condition, and it's going to oscillate, but each time it oscillates, it's going to oscillate more and more and more. It's something that's just out of control. I hope that helps, and thanks for watching.